I guess we can start the talk. I'm very happy to introduce Anita's talk because most of you know that she was a student here. So I hope she feels to be back at home after some wandering across Europe and United States. So since I know she has a few slides presenting her work and different positions she got. So I prefer to leave her to talk about her new results. And I think we can be happy. We are happy to have here also as a new researcher of the Observatory. This is why she's going to go with this talk in order to be more in touch with us. And so thank you. And I leave the phone. The microphone. Lo posso spegnere? Okay. Because we are in connection with Asiago. This is the reason we are using the microphone. So,
okay. Thank you. Thank you very much. I'm very happy to be here today, and I'll take the occasion of this seminar to introduce myself to all those that don't know me yet. So I will introduce myself by discussing, first of all, my science, the science topics I'm working on, and towards the end of the talk, I will also discuss a bit about other topics that are very interesting to me. Namely, I will discuss some instrumentation projects I'm involved with, and a bit of the outreach projects that I'm currently leading. So this is the reason for the title, Clumps in high-redshift galaxies, which is the science I'm working on, and more, namely the instrumentation and the outreach I will discuss towards the end of the talk. So I would like to start describing a bit what is the path that brought me here. So I studied here at the University of Padova for the bachelor, and for the master as well, after spending a few months at the University of Minnesota in the US with a studentship, working on my master thesis. I then came back to Padova to discuss the master thesis under the supervision of Enrico Corsini and Elena Dalla Bontà from the University of Padova, and Claudia Scarlata from the University of Minnesota. I then moved to Paris, where I got the PhD at CEA in Saclay, under the supervision of Émeric Lefloc and in tight collaboration with Emanuele Daddi and Frédéric Bourneau. And after the PhD, I moved on. I went to Munich, in Germany, at the European Southern Observatory as a research fellow. So the fellowship in Munich works this way. Fellows are supposed to work for 75% of their time on science, and the remaining 25% is on duties that need to be helpful for the observatory. So as duties, I was spending 40 nights every year in Chile, in Paranal, operating the very large telescope instruments. And in particular, I was operating the instruments on board of UT4. So at that time, Muse, Symphony, and Dokai. And towards the end of the fellowship, I was also operating the UT2 instruments, so X-Shooter, UVAs, and Flames. So this has been an incredibly enriching experience. It opened my eyes towards observations and instrumentation as well, so I really enjoyed those years. And finally, since November 2019, I'm now here as a researcher at INAF. So I will start discussing the science topics I'm working on, just putting the science into context, and then I'll move on describing the details of the research I'm carrying on. So in the Lambda CDM framework, the universe is supposed to start with a Big Bang, an incredibly dense phase, and with a moment of inflation where the universe started expanding. And then the universe cools down, the first atoms start to recombine. Some photons are emitted, and we can still see their footprint as the cosmic microwave background. About 400 mega years after the Big Bang, the first clouds of hydrogen start to collapse and the first stars start to form. The first galaxies follow then. And about 3 giga-years after the Big Bang, we have this peak of the cosmic star formation rate density, where the galaxies are the most active during the history of the universe. And then the star formation rate density declines towards later times, and we arrive, let's say, at the universe as we see it today. So the phase of the universe in which I'm the most interested in is this one. So the formation and the evolution of galaxies about 3 giga-years after the Big Bang. So my research field is galaxy evolution, and it's quite well known by now that there are two main populations of galaxies. So star-forming galaxies on one hand that are forming stars very actively, and quiescent galaxies or passive galaxies on the other hand, where the star formation basically stopped. And it is also well known that both these populations of galaxies evolve with cosmic time or equivalently with redshift. And this becomes clear when we compare these panels. So for the star-forming galaxies, for example, this is a typical Milky Way-like galaxy observed in the local universe. So it has a very regular morphology with some spiral arms, a central bulge, a relatively low gas fraction of 5 up to 10%. If we look instead at the typical progenitors of Milky Way galaxies, at redshift 2, they have these irregular shapes. They don't really show a central bulge. They have very high gas fractions, up to 50%. And their morphology is dominated by these blue knots, which are giant star-forming regions and typically are called clumps. So it is still unclear what are the mechanisms that bring us from these progenitors to these Milky Way-like galaxies. And similarly, it seems that also quiescent galaxies evolve with time, with more compact passive galaxies at higher redshift with respect to the local universe. So again, the mechanisms driving the evolution of passive galaxies are not completely clear. And I worked on both the evolution of star-forming galaxies and quiescent galaxies. But for the talk of today, I will just focus on the first topic, so the star-forming galaxies results. So in particular, the main open questions that I would like to address with my work are the following. So first of all, how do galaxies assemble their mass? So what's the role of galaxy-galaxy mergers? And what is the role of secular processes, such as the accretion of cold gas from the cosmic web? So what triggers and quenches later on the star formation? And what is the role of stellar feedback in these two processes? What physical processes drive galaxy evolution? So as I said, how do we go from these progenitors at redshift 2 to the local typical galaxies we observe? How do galaxies assemble their bulge, their nucleus? And how are globular clusters formed? And the view angle I'm using to address these questions is a bit particular. So I'm trying to address this question by studying these giant blue knots that are dominating these images of redshift 2 star-forming galaxies. They're, as I said, giant star-forming regions. They're ubiquitous at redshift 2, and they're typically called clumps. So I will refer to them with this term in the rest of the talk. They have stellar masses of 10 to the 7 up to 10 to the 9 solar masses. They can make up to 50% the total star formation rate of the host galaxy. And they have sizes of 1 kiloparsec or less. So their sizes are still highly debated. They're extremely hard to measure. And the reason is the following. Most of the clumps are still unresolved, even with the best images available, which are HST images or ground-based AO-assisted observations. And so the best quality data are needed to really study these star-forming complexes. And this becomes clear when we compare the two panels. The top one is an HST image, and the bottom one is a symphony image. So symphony is a VLT instrument. In this case, no adaptive optics was used. So as you can see, the same galaxy appears just as a big blob, and all the small star-forming regions disappear in this symphony image. So we really need space-based observations or AU-assisted ones to start studying these clumps. And still, sometimes it seems they're not enough. Better resolution is needed. So studying clumps can shed light on the open questions that I mentioned before for the following reasons. So they could help us to understand what is the contribution of galaxy mergers and secular processes in the evolution of galaxies. And so there are, in particular, two different scenarios that have been proposed for the formation of these clumps on the simulation side. So on one hand, these clumps could be remnants of satellites that merged with a host galaxy. So we are in this case, and in this case, these star-forming regions still keep their small dark matter halo. So they're just the nucleus, basically, of the satellites that got stripped. In the other possibility is that they come from secular processes. So galaxies accrete cold gas from the cosmic web. The disks of the galaxy become gas-rich. They locally fragment, collapse, and form in situ these star-forming regions. So in this case, there is no dark matter, let's say, associated to these star-forming regions. So tackling what is the formation of the clumps will tell us what is the contribution of mergers and secular processes in the buildup of the galaxy mass. Also, they can help us to clarify how star formation proceeds at high redshift. So here, for example, I'm showing star formation rate in the y.
Ha deciso di spegnersi così.
Okay. Okay, so we can use clumps to directly constrain the strength and the role of stellar feedback on a specially resolved basis. And this is critical to understand what is the role of clumps in the evolution of the galaxy, whether they play a role in the structural transformation of galaxies or not. So in particular, some simulations tell us that the clumps are quickly disrupted by stellar feedback in less than 100 megayears, and so they play no role, they're just transient features. Other simulations instead, on the contrary, tell us that clumps are massive enough to remain bound, survive feedback, and eventually migrate inward towards the center of the galaxy and form the galaxy bulge. So this is what we're seeing, for example, in these simulations. So in the left part, you see a galaxy face-on. On the right part, you see the same galaxy, but with an edge-on view. So the disk of the galaxies gets rich. As I said, it starts to fragment, collapse, form the first clumps. And then the clumps migrate inwards due to dynamical friction and gravitational torques. And at the center of the galaxy, at the center of the potential well, they start to coalesce and form the galaxy bulge while thickening the galaxy disk. So in this case, they would play a fundamental role in the evolution of the host galaxy. In this process, they might also fuel the central black hole, and, well, possibly, they could possibly be related to the formation of globular clusters. So for all these reasons, I think the clumps could give us an insight on some of these questions related to galaxy evolution, and for all these reasons, I'm studying them. So the way I'm studying them lately is by using HST imaging in different bands, near-infrared and UV, and also slitless spectroscopy. So we are in the ultraviolet and visible regime, and this image that you are seeing here is the pointing of the slitless spectroscopy on, with the Wildfield camera 3. So due to the lack of a slit, different orders of different spectra are overlapped, so the analysis of the data is very tricky. But the advantage is that due to the lack of a slit, the shape of the emission line is really the morphology of the galaxy. So this allows us to directly compare spatially resolved emission line maps with spatially resolved continuum maps coming from the imaging. So from the rest frame optical imaging, we get a spatially resolved probe of the stellar mass distribution in the galaxy. From the spectroscopy, instead, we get a probe of the star formation distribution in the galaxy disk. And so far, typical surveys have been addressing or observing the star formation distribution by using UV imaging. But the UV only allows us to probe the older stellar populations, older than 100 megayears. If we really want to study the initial phases of clump formation, then we need spectroscopy that allows us to study stellar populations with ages of 10 megayears or younger. So for this reason, I'm using spectroscopy as well. So to look for these clumps, I'm simultaneously using continuum and emission line maps. I subtract a diffuse disk of the galaxy, and in the residuals, I look for residual structures, and I call these clumps. So at this point, I have a full catalog with the fluxes and the location of the clumps. So I repeated the procedure for about 50 galaxies in our pointing. These are the continuum maps, and these are the emission line maps. So if I blink a bit between the two, you can already see by eye that for some of these galaxies, the continuum and the emission lines have quite different morphologies. So it is critical to have both to have a comprehensive view of these galaxies. And one of the first characteristics that we noted in this sample is the following. There seems to be two different populations of clumps, some that are compact and others that are extended. And here there's an example. So this is a galaxy with a diffuse disk and then several blobs. Some of them can be modeled with a PSF, so they're unresolved, but some others have to be modeled with a Sersic profile. They're extended, they have effective radii of about 2 kiloparsec, and Sersic indexes of about 1. So they're consistent with being like small galaxies or small disks. So in the rest of the analysis, I will keep these two populations separated, and I will investigate their physical properties and their origin.
What's the redshift of these galaxies?
Between 1 and 3. Yeah. So the physical properties I'm looking at here is the stellar mass of the clumps in the y-axis and their age on the x-axis. So in blue, I report the disk of the galaxy. In red, they are the extended clumps. In black, there are the compact clumps. So already by eye from here, you can see that the extended clumps have very similar properties as the underlying disks. They're more massive and they're older, whereas the compact ones are less massive and younger. And this becomes clearer when we look at the distribution. So that's the distribution of stellar mass, and this is the distribution of the age. In the top panel, the cross is the mean of the distribution, and the ellipses report the standard deviation, 1 sigma and 3 sigma. So it's clear that compact clumps are less massive and younger than the extended ones that have rather similar properties as the disks. So there really seems to be two different populations, and the next step is to try to investigate how they're formed. And for this, I'm comparing with numerical simulations. So in particular, I'm using the Vela simulations from the group by Mandelker and Deckel. So this is an example of their galaxies. They have a sample of clumpy galaxies. They localize the clumps, and they divide them in two groups based on their dark matter content. So it's a very different selection at the beginning with respect to the one that we can do in observations. And they divide the clumps that are formed in situ due to the fragmentation of the gas-rich disk that don't contain dark matter, as I said at the beginning. And they have a second population of ex situ satellites that merged that have still their own dark matter halo. And these are the black and the red distributions here, again in stellar mass and age. And when we compare the mean of the simulated distributions with the mean of our own observed distributions, we get the gray and the pink lines. So for the age, simulations and observations seem to be in remarkable agreement. For the stellar masses, the agreement is, I would say, qualitative, even if quantitatively there is a small discrepancy, and there are a few reasons for this. I will not discuss them now, but if you're interested, we can discuss about them later. But I would say that, at least qualitatively, simulations and observations have very similar properties. So from here, I would conclude that the compact clumps population in our sample, which are about 70%, are likely formed in situ due to secular processes, whereas the remaining 30%, which are the extended clumps, are likely formed ex situ, and they're satellites that merged with a host galaxy. Looking a bit more into this aspect, I also looked at the distance of the two populations with respect to the galaxy center, and this seems that the satellites are found in the outskirts of the galaxies on average, and a bit farther away with respect to the compact ones. So this is consistent with the merger scenario. And the other possibility is to look at the mass-metallicity relation. So here in the x-axis now is metallicity. So the solid line is the mass-metallicity relation of redshift 2 disks. And as we can see, our disk, which is the blue point, is well in agreement with the expectations. Whereas the compact clumps, those that are formed in situ, have much higher metallicity with respect to the one predicted by the relation. So in particular, the star are the typical dwarf galaxies. So these clumps in the local universe up to redshift 1. So these clumps have masses that are similar to dwarf galaxies, but much higher metallicity. And I would interpret, and in particular, their metallicity is comparable to the one of the disks. So I would interpret this as the compact clumps being formed in situ from the gas that was pre-enriched by star formation. So I would say this confirms the scenario that 70% of the clumps are formed due to secular processes, and the extended ones, 30%, are satellites that were stripped. So the next step and the next big question is, what is the fate of these clumps that were formed in situ? So are they disrupted by stellar feedback, or can they survive and play a role in the formation and evolution of the galaxy? So to look for their fate, we can look at possible age gradients with respect to the center of the galaxies. So this is age, again, in the y-axis, and in the x-axis there is the distance of the clumps from the center, normalized by the radius of the galaxy. And there are a few points that I want to make in this plot. So first of all, it seems that there is a population of star-forming regions with ages of 300 up to 500 megayears. So it seems that at least some of them can be long-lived and survive stellar feedback for hundreds of years. The second point I want to make is about the gradient. So if clumps survive stellar feedback, from simulations, they're expected to migrate inward due to the friction and the torques. So in this case, we expect older clumps to be preferentially found at the center of galaxies rather than in the outskirts. And indeed, this is the prediction of the simulations, so the green crosses. Our points, again, are the black ones. And I would say there's no trend observed in the observations. That's really scatter what we see. And this is in agreement with other literature results, such as the ones by Guo and collaborators, that I report here with the yellow symbols. So the difference between our surveys and their survey is the presence or not of the spectroscopy. They are only using the imaging, so they're losing all this population of young clumps, but still they get a flat gradient as we are. And in particular, this is the plot from Guo and collaborators. So at redshift 2, the gradient is flat. Interestingly, they have a bigger sample than we do, so they can also be in redshift. So at redshift 1, they start to see a gradient, and at redshift 0.5 as well, they see an age gradient. So it is unclear what is happening here. There are a few possibilities. Either a signature of migration is not seen yet at redshift 2, either we have too big uncertainties on the age that are masking a gradient here, or my favorite option is that probably the spatial resolution is still not enough. So at redshift 2, we are missing all the central kiloparsec of the galaxy, where the gradient expected from simulation is the steepest. If we go at redshift 0.5, the spatial resolution is improving a bit, and then we can start to disentangle better the different star-forming regions, and hopefully to start to see the gradient. So I would say better data with better resolutions are needed to answer this question about migration. And the last point is about this population of young clumps that we start to see in this survey. So in particular, we can start to use the average number of young clumps in our sample to give a statistical estimate of the clump's lifetime. So to do so, I consider the number of young clumps in our sample and the visibility window. So namely, the period of time during which a star-forming region can be considered young. And at this point, we get the clumps formation rate. So the number of clumps that are formed per galaxy and per gigayear. And we get about 10 clumps per gigayear with low masses and 2 clumps per gigayear with high masses. And now if we compare this number with the average number of old clumps at a given mass, we get the statistical estimate of the lifetime. So we obtain lifetimes of about 145 megayears for the low mass bin and 650 megayears for the high mass bin. So it seems that for clumps with masses above 10 to the 8, which are the ones that we can really observe in our survey, it seems that they survive stellar feedback. And so this would be in agreement with the simulations indicating that clumps have at least the most massive clumps have an important role in galaxy evolution. Clearly, as I said, this is a statistical approach. The next step is to directly look at single clumps and constrain the feedback on subgalactic scales. And we have recently started to do that by using data from HST, MUSE, and Symphony. So Symphony is here in the near infrared, observing a local cluster, and in particular 2 galaxies that have been magnified by these local clusters. So these are the two galaxies. We have 3 images for each one. One is more compact, the other one is really clumpy. So we're now focusing on this clumpy galaxy. In particular, Edoardo Ianni is leading this project. He's a student here in Padova. He was working with me during a studentship at ISO for 1 year. Here in the background, you can see the HST image of this clumpy galaxy. And then on top, the blue is H beta, the yellow is O3, so white is O3, and the black is Lyman alpha. So the H beta, as expected, is following very well the UV continuum. The O3 is slightly more extended, and the Lyman alpha is very extended and offsetted, which is typical at this redshift. So here in the panels, you can see the spectrum, the different emission lines. So in particular, now Edoardo is fitting the Lyman alpha profile with the radiative transfer models, trying to constrain the mass outflow rate and the strength of the stellar feedback, trying to understand whether these star-forming regions can survive or not. And thanks to the richness of the MUSE data, we can also have access to other UV lines, such as, for example, the carbon-3 doublet that we see here resolved. So from the ratio of the two carbon-3 lines, we can get an idea of the density of the gas, and as well the carbon-4 doublet that here we see in absorption. So this is a work that is ongoing. More results are coming soon. And in particular, last week we got some ALMA data targeting the continuum and the C2 emission for this source. So the idea is to look, again, the resolution is 0.2 arcseconds, so comparable with the resolution of all the other data set. So we can start to see what is the dust distribution in this source, spatially resolved, and also to constrain the molecular gas at this redshift. So to estimate the molecular gas, we are planning to use the carbon-2 emission, which is quite of a different decision with respect to what has been used in the literature so far. So usually the carbon-2 is used to trace star formation at high redshift. But recently, we have tried to understand whether we can use C2 as an alternative gas tracer with respect to CO and dust, which are the traditional tracers at this redshift. So I'll spend just a few words on this. So we get carbon-2, which is a far-infrared line, when we have UV photons. So basically when we have star formation. So the UV photons hit the dust, and at this point we have a double effect. On one hand, the dust emits the infrared continuum. On the other hand, some electrons are stripped from the dust grains, they hit the gas, and when the gas cools down, we get cooling lines, such as the carbon-2. So carbon-2 is one of the brightest infrared lines, so that's very convenient to observe at high redshift, and it's well covered by the ALMA bands. The disadvantage is that the ionization potential that you can see here of carbon-2 is lower than the ionization potential of the neutral hydrogen. So carbon-2 can arise from different gas phases, and we need to be a bit careful in this respect. However, we tried to look, we got some ALMA data, so here in the sub-millimeter regime of galaxies at redshift 2. These are the red points, and we are comparing their C+ luminosity with their molecular gas, including also points from the literature at redshift 0 and at higher redshift. So there seems to be a linear relation between the C+ luminosity and the molecular gas from redshift 0 to redshift 5. Where the molecular gas was estimated from CO when available or dust. And at this point, we need to estimate the conversion factor that we call alpha C+, that is needed to go from C+ luminosity to molecular gas mass. So it seems that this alpha C+ conversion factor doesn't depend on redshift. This is what you see in this plot. And we have similar plots with metallicity and the star formation efficiency. So it seems that the conversion factor doesn't depend critically on redshift, metallicity, and main sequence or starburst behavior, although the scatter is quite big. So this needs to be taken into account. So it seems the carbon-2 can be an available tool to estimate the molecular gas mass at very high redshift, let's say redshift higher than 2, 3, as an alternative to the fainter CO and dust. So what is my wish list for the future, and what are the future plans? So what I would like, as I guess many here, is data that are with a better sensitivity, spatial resolution, and statistics. So thanks to deeper data, we can get lower mass and lower star formation rate star forming regions. Thanks to the better spatial resolution, we can start to constrain their sizes, understand whether they have substructure or not, and with the statistics, we can get a complete census of young and old clumps. So to achieve these goals, we can use some of the next generation facilities, in particular NIRCam and NIRSpec on JWST, Harmony on ELT, and MAVIS if it's accepted on the VLT. So thanks to JWST, we can get samples of more than 500 galaxies, a ratio between 2 to 5, with a very good spatial resolution of 100 parsec that is unprecedented for field galaxies. With Harmony, we can tackle their emission lines, H-alpha 03, O2, and with MAVIS, we can get complementary information in the UV, so for example, the Lyman alpha for these sources. And for example, this is a galaxy observed currently with HST, so the best images we can get. And this is a simulation with NIRCam, so you see that you can really start to distinguish the single star-forming complexes and with much better detail. So to get ready for the next generation of facilities, I've been looking into Harmony and MAVIS in particular. I was part of the ESO working group and science team for MAVIS, so I wrote science cases for the Clumps, and now I'm hoping to get still into MAVIS from the INAF part. And for Harmony, we started last summer with the students to do some simulations of clumpy galaxies, some mock clumpy galaxies. You see an example here, so we simulated a disk with some point sources on top. We ran it through the HSIM simulator, so that's the Harmony simulator, and we get in output the observed mock cube from Harmony. So we are now trying to understand what are the physical properties of the clumps that we get in output, and down to what limits we can start to constrain masses and star formation rates and sizes, and so on. Again, I'm in contact now with the team that is working here on Mikado, because I think there's a lot to exchange about the PSF reconstruction between Harmony and Mikado. So I hope to get involved with that as well. And before concluding in the last few minutes, I would like to briefly talk about another topic that I'm really passionate about. It's outreach, and I would like to discuss a couple of the biggest projects I'm involved in and I'm leading right now. So on one hand, I've started to organize a science festival in Mantova. So this is something we have done already in different countries. In particular, while I was at ESO, I was leading the organization of the Fédérations in Paris. So the idea is to bring to Mantova similar workshops and videos and conferences. These are some of the pictures that were taken at the Science Festival in Paris. We reached about 1,000 people in a weekend between adults and kids. And it has really been a great experience. On the other hand, a bit more ambitious project is what we're calling the Audible Universe. I'm leading it together with Chris Harrison. So Chris Harrison has started already to do some outreach projects to make astronomy available for visually impaired people. So he was creating 3D images with 3D printers from astronomical images, so they could touch and get an idea of what images we are looking at. And also, he was doing some sonification of astronomical images. So I brought an example, let's see if it works, of a sonic that transformed it into sound. I would like to make you hear this. Let's see. No. Let's try again. Well, it was working when I was... Is it? Yes. Okay, so this was done. Sorry? No. So this was done for outreach purposes. Now the idea is to bring it to the next level and really try to understand whether sonification can be used for educational purposes and whether we can retrieve information that also for people that are not blind, but further information with respect to what we are used to retrieve with the sight. So whether we can use the sound together with the images for research purposes. And to this aim, we are building now a team of astronomers, some visually impaired people, social scientists, educational psychologists, sound engineers, and musicians. So the idea is to have a workshop all together next year and try to decide what are the next steps and start to do some research in this sense. So these are the main projects. I discussed some of the science I'm doing, some of the instrumentation projects I'm involved in, and some of the outreach projects. In particular, for the Science Festival in Mantova, I'm lacking people. So if any of you is interested, we can discuss about it. And in general, if you have any questions, any interest, please come to me and talk to me. I'll be very happy. Thank you. Questions?
I have two questions. One quick. Did you apply correction for attenuation, internal dust attenuation on your images?
Yes,
Okay.
we did in most of the cases. So depending on the redshift of the source, we cover different emission lines. Depending on the ratio, on the source, from line ratios we can get an attenuation. The problem is we get an average attenuation, so galaxy integrated, because on a specially resolved case, that's very difficult.
Okay.
There are other works in the literature that are using specially resolved SED fitting to determine the attenuation. And they find that in most of the cases, the average galaxy integrated attenuation is comparable to the specially resolved ones. So we are assuming it's the same, but clearly there could be some differences.
And the second question is boggling me for the whole time, for many years already. Where are clumps now? Why don't we see in today's galaxies some large clumps features? We only see the complexes of star-forming regions, spiral arms, small regions, big regions, and so on, but no big, huge clumps.
So I guess the question is not bothering only you, but the whole community. Observationally, it's still unclear, I would say. Some simulations indicate that we can form these clumps when the gas fraction is very high, so at high redshift. Then in the local universe, the gas fraction is lower, the turbulence of the gas also is lower, and then it's more difficult to form these clumps. And so we form rather these giant molecular clouds that have very different masses and sizes. The other possibility is also that the central bulge is somehow stabilizing the disk, and also that could prevent the formation of the clumps.
Thanks for the nice presentation. Some 10 years ago, there was a lot of interest, in fact, on the clumps because they offered a new way of forming bulges via the migration of the clumps due to dynamical friction. However, the clumps were first discovered in emission lines. And only later there was an attempt to measure how massive they are and whether they are gravitationally bound, because only if they are massive they could in fact experience the dynamical friction. However, as you also have shown on one of your first view graphs, the clumps appear only in emission lines and not much in the continuum at all, indicating that they are more clumps of star formation as opposed to clumps of mass. And so this idea of the migration has lost a little bit of momentum in more recent years. And the other thing that has been found more recently, using in fact highly stretched and magnified few cases with gravitational lensing, that the clumps that typically on a resolution of a kiloparsec have sizes, there are a few per galaxy. At a resolution of less than 100 parsecs, they turn out to be 50, 60 clumps. So the big clumps we see are actually, or likely to be in most cases, clusters of smaller clumps. What do you think about this?
So I would say you're absolutely right in both cases. To answer your first comment about the fact that the clumps are much brighter in emission lines than in continuum, yes, that's true. However, well, so they're highly star-forming, so it's definitely easier to detect them in the UV or in the emission lines. However, we detect them also in the continuum, not only us, but also other surveys like GUO and collaborators. And so this is an example. That's the same galaxy, emission line, and continuum, and we see the same three substructures in both cases. Then we have cases as well where we only see them in emission lines or in continuum. So these differences, I attribute these differences to age differences. So the youngest clumps appear mainly in the emission lines and not in the continuum, and vice versa. The old clumps appear in the continuum and not anymore in the emission lines. It could also be a difference of specific star formation rate, for example. Clearly, it's difficult to detect them in the continuum because if they have masses of 10 to the 8 solar masses, we need very deep continuum. So what I hope is that going deeper on the continuum, for example, JWST, ELT, we can go to lower masses, lower than 10 to the 8, and we can really start to see and build, for example, mass functions and so on. About the second comment on the size of clumps, yes, again, it might be that this kiloparsec size is due to a resolution effect, as I was mentioning at the beginning. So there are two approaches that are now followed. One is to look for local analogs of high-redshift clumpy galaxies. And in that case, they find that these big clumps break down in substructures that have hundreds of parsec sizes. And in less galaxies as well, the size ranges goes from 200 parsec to 500 parsec. What is unclear to me still is whether this substructure is bounded. So if it's a big cloud that fragments and form these bounded small clumps, or whether they're just random associations. Because I think it makes a big difference. If they're bounded, they can still be considered as a single complex that might survive the feedback. If they're just random associations, then fine, probably they have no role and they're quickly disrupted. But that to me still needs to be proven.
Okay, it seems that Virgo simulation has a hard time to reproduce the massive end of the population.
Yeah.
So did you discuss with the simulators on this issue?
I am. It's not easy. It's not only Eagle, also Illustris, also the most recent TNG simulations. They don't reproduce the clumpy galaxies. I think it's a big issue, and it's still unclear to me whether this is due to the feedback recipe that goes into the simulation, or the initial gas fraction that is assumed in the simulations. So I'm currently working with Frédéric Bourneau, Jeremy Fench. They have some isolated galaxies, and they vary the feedback recipe and the gas fraction and see what's the effect on the morphology. It's still work in progress, and it's quite tricky. But I agree. I think we need predictions from the simulators changing feedback and gas fractions.
Curiosity, do we have any kind of information of the IMF, possible IMF of this kind of block?
It's a bit tricky. Yes. At the moment, no. It seems that at least in the youngest phases, these clumps are highly star-forming. They're probably star-bursting. They could have a top AV IMF, but it's still very much unclear.
So in addition to the size issue that Alvia was mentioning, there is another caveat that is burdening me for already some time. Because when we are trying to estimate the ages and the masses of low redshift clumps, we encounter a problem that is also your problem. That is that you're not measuring the stellar mass of the clump, you're measuring the stellar mass of everything that is along the line of sight. So it makes sense that the ones that are closer to the center of the galaxy are more contaminated by older stellar populations, which will be there. There will be older stellar population than your clumps. And the same, she doesn't subtract the age. When you compute the ages, I guess you compute the SCD fitting from the photometry.
No, it's a bit different. But I'll let you finish and then.
Okay, so anyway. So it's really tricky, if not impossible, to get ages and stellar masses of the clumps. So the question is, how do we do it at high redshift and at low redshift? How can we get the right numbers?
Yeah, again, I agree. It's very tricky. And I was also thinking about that. So the way I'm using here is to subtract the diffuse disk. So I'm subtracting a Sersic profile. And then I look in the residuals. And I fit simultaneously, as a second step, the disk plus these residuals. So this is my way of disentangling what is the disk that is very bright in the continuum and near-infrared bands, and what is the clump. So the way I'm using to yes, the way I'm using to measure the age is not SED fitting. I don't have enough bands to do that. And also, at young ages, I don't really trust the SED fitting for 10 mega years or younger. So the way I'm using is this one. I'm computing the equivalent width of each clump, so line divided by the continuum. And then I need to assume some stellar population synthesis model, so I'm using Starbus 99, and this gives me the age. Clearly, this depends on the star formation history that is assumed, so I'm using 3 different star formation histories in each case, and then I get error bars based on the different star formation histories. I'm using an instantaneous burst, a continuum star formation, and the star formation history coming from simulations, with an initial burst and then a decrease of star formation. It clearly depends a bit on the IMF. I'm using a standard saltpeter IMF. If I use a top heavy, this moves a little bit, but not critically. So this is the way I'm using the equivalent width.
So you can only measure the stellar ages where you have lines in emission from the H-beta emission line.
Sorry?
You can only measure the stellar ages if you have line in emission.
Right. Otherwise, I get upper limits.
You cannot get older clumps in this way.
I get upper limits. Yeah. Sorry, lower limits. Lower limits. Yeah.
In the next 10 years, so I cannot.
But sorry, this is complementary to what Guo and the others did with the SED fitting. Yeah.
So these galaxies are also very dusty, and the dust is not homogeneously distributed, right? So what if some of these clumps are not clumps but holes in the dust? How can you?
Well, this was exactly the motivation for this ALMA proposal that got accepted. So in this case, this is a lens galaxy, so we can go and look really on hundreds of parsec scales, a bit better than the field galaxies. And the idea here with ALMA is really to put the dust continuum together with the UV light that we observe from HST with the same spatial resolution, and try to understand whether the dust is homogeneously distributed, whether there is some dust, how it is distributed, and whether these clumps are physical regions or just, yes, holes in the dust that lets the UV light come through. Yeah, so coming soon, hopefully.
So it will be the first time that this thing is done, or
I've
there are
not
already
seen other works. So there was a work by Desoj Zavasky on the cosmic snake. So they were looking at CO. And for the first time, they start to see some of these clumps in CO. It was very tricky. We tried as well with Anna Cibinel, and we couldn't detect the CO. That was a bit scary. But there are several reasons. CO is faint. It could be that it's consumed already by the star formation. So Mirka managed to see the CO, sometimes together with the with the UV. They don't have emission lines. Together with the UV, sometimes they're not cospatial. But to my knowledge, they don't have the dust emission. They didn't show that, at least. And there's nothing else to my knowledge at this point with this resolution. Yeah.
Okay, Anita is in the second floor of the observatory. If you want to talk with her, you can go. And then thanks again to all. And,
thank you.